We will start a new chapter. In this class, we will discuss the sampling distribution and different sampling techniques, and we will go over central limit theory. So in the previous lectures, we have spoken about different probability techniques. In a probability, you want to predict a setup from known history or from known experiments, but from now and on, we will talk more about the statistics. So in statistics, we want to compress the population into a small setup, for example, like a mean, and we want to take from these parameters like the mean, the median, the mode, if we are talking about parametric statistics, standard deviation and the range, and how much they can give us an information about our population or about research and experiment. Then finally, we'll spoke about design of experiment. In design of experiment, we will have two loops. So we will start with induction. We will set up the questionnaire and the problem for our research and experiment. And then we will use some of the statistics tools to have a deduction about the information. And if it's help us to answer this question, we can close our loop. But if not, it should direct us to another direction. We will starting the induction research again until we find a satisfactory answer for our research question. So what is the goals about today's lecture? So we will explain the sample and learn different types of sampling technique. Moreover, we will cross over the central limit theorem and see how it will help us doing our research, and also will help us for the sampling technique. Also, we will have an Excel training. I am open to do it via Minitab or RStudio or any other softwares. But I encourage you to use a software for submitting the exercises and the homework. So why sampling is very important? So imagine that your manager asks you to gather the information about the students who attending at YSU, and ask you about the collecting the demographic information like their height, their age, their sex, their parents' work, etc. So it's very time consuming, and it's mostly invisible. It applies also to experimental lab. So you will have a limited time to do some experiments, and like as we're living today is like with COVID-19 and the pandemic, so we don't have much time to see all the scenarios. So you need some representation through the sampling, and also you have limitation. As an engineer, the cost plays a higher role within your decision. So, and you cannot do as much experiment as you want. So you have limitations for the budget. And sometimes it's very possible to collect all the data set you want to. So like, imagine you are working with a machine and you want to measure the production time for the machine, and the manager asks you to do a model for the time that take the machine to process. If you want to take all the factors, it's near impossible. And some models end up with 21 and plus variables. In most scenarios, you might end up with more variables. So it's very hard to quantify all these variables. So we need to to have some control over them. And some of them have a trivial effect, while others having a significant and economical impact on our test. So in mechanical engineering, we have destructive test and non-destructive test. And you will end up in many times performing destructive tests, such as tensile test. Even like if you are talking about a human research, so sometimes you will not guarantee that the surveyed will retain again, or there is some confidentiality. So it can consider to be a destructive test, and you will not have a control over all the variables. So we need some sampling technique to cross over all these issues. And sometimes the samples are adequate to represent the population. So let's say you want to see the communication within a flat organization and the tall organization. And you can just only survey a few members, and they can give you a good indication about the communication over there. So the samples sometimes are adequate enough to represent your population, and they are more economic and take less time to perform. So there is two types of sampling. The first one is the probability sampling, and the other one is using different judgmental techniques. As an engineer, usually we will more rely with a probability sampling, but sometimes you need the other techniques to use some marketing surveys, or to introduce a new knowledge that is not covered by other texts or research. So in the probability sampling, simply you select an item or a person that have a high likelihood to be presented by the population. So the simplest example, that you are on assembly line and you just pick up one of the products at a very random time. So this product might be the first one have been assembled, or maybe within in between times, or after inspection processes, etc. So this will be having an equivalent likelihood to be presented in the sample. But as I mentioned before, samples need to be smart and should be reasonable to have a likelihood that they present the population in a good manner. So there is also subcategories about the probability sampling. So we have the simplest form, and the most accurate form is the simple random technique. We will just collect the data arbitrarily. There is no prerequisite about it, and this is the most accurate one, but it has some problems involved within, like the nature of the sample. Is it like we have a sample with replacement or without replacement? So that's plays a huge role. So you might end up with picking the same sample over again if it's with replacement. Then we have another one can solve this problem, which is the systematic random sampling. So you give IDs for your samples and you select a K number. But it sometimes might have a behavior within this technique, so it will have a less reliability than pure simple sampling. Then we have another technique. So sometimes when you selecting a random samples, you will end up with selecting a certain group, and the other groups will not have a representation. So for example, you are talking with different students, let's say at the beginning of each one of the class, but for some reasons, let's say senior students who's have a time to come before the class because they have a knowledge about the university. So you will end up just surveying senior students. So when you pick up a stratified, so you will have subgroups and make sure like each member of your population have a chance to be represented in your sample. The problem with this technique is you need to have a pre-knowledge about your population, and also sometimes it will have some certain of bias. Then we have also cluster sampling, which is very close to certified, but instead of that, we have just only a few subgroups instead of very complicated groups, and also both of these have some limitations. So let's start with the random sample. So we just select an item, very arbitrary, and it's have a good chance to be included. So for example, you are working with Nitro Industries with 845. You want to pick up 52 employees that could represent in the sample. So let's say you are looking for some people can be surveyed. So the simple thing is you just pick up a random ones. So you can make, for example, a list for your employees, assign a number for each one of them, then just put them inside a wheel, then pick up their number, and that's it. It's very similar to the lottery process. So each number have an equivalent chance to be presented. So you might end up with a winning ticket like the Powerball, or you just lose as everyone else. So this is the simple sample. When we are talking about systematic, so we choose a kth member. So for example, for the same previous example, so we set up with kth. So since we have an 845, we divided by 52. So every 16 employee, we can, this is the number of K. And then, for example, you select number 10 to be the first employee to be surveyed. Then we continue with number 26. Then again, you add 16 each time until you have the full sample. In a stratified, it's more complicated. You need to have some knowledge about your population, and usually these demographic informations may play a role in your statistical analysis. So it depends. For example, if your gender, your material status, for example, the salary, the managerial level plays a role in your survey, you need to have the stratified sampling. If you are just only want to skirmish your population, so you don't need to go over all of these, but you might end up investigating them after your first result as inductive technique. So in this scenario, we just have some stratum for each population, and we divide them into subgroups. And then finally, we're trying to collect a representation for each group. So the problem is sometimes, let's say, you are trying to make ethnicity as a strata, and you don't have the exact representation or their percentage in your original population. So that's sometimes gives some problematic, but even though still, if you have this, again, a simple random technique, so you might up having more representation for your population. Of course, it depends on the sensitivity of your research. So in a laboratory, so these can be changed. For example, who's your vendor? Where is this material shipped from? So they might play a role from my experience. So one of the alloying elements we shipped from steel was exported from India, the other one from China, and we have also some local vendors from Saudi Arabia. We didn't find a good alloying percentage from Saudi Arabia. And so they asked us to increase the sample. And they didn't agree with our results, which ended up to use all their shipment as a sample. So like we used all population to prove that their alloying elements weren't good enough for our yield, and this is make a large problem. So sometimes in statistics, sometimes people doesn't believe in sampling. So you need a large sample enough that you and your customer will agree on. And this will be investigated in this topic. Then we have the cluster sampling. So in a cluster sampling, instead of having a very complicated stratified group, so then we will just have small clusters. So it might be like in 2 levels, or might be just only 1 levels, retaining to the geographic boundaries between the surveyed people. Or sometimes you are trying to distinguish between different steel alloys, so you are just only looking after carbon steel alloys, and this is make your life way easy. So there is another methods, non-probability sampling. One of them is judgmental technique. So you are experienced in your field, and you want to investigate something. So you might be ending up with just only investigating one type of alloy instead of searching the whole possible combination of your alloy. So this will be having a judgmental. Sometimes there is just only few groups of expertise, and you don't need to survey the whole population. So you know these people, and you came to them and they can explain the information you want. So this is also a non-probabilistic, because you reach out a certain people. Sometimes there is a snowballing technique. So you don't have enough information to start your population. You don't know about your population. So you come to the first survey, and this guy will lead you to another one, and then the other guy will lead you to another one, and the ball keep rolling, and then you will have enough information about the population. So this is non-probabilistic sampling technique. And also there is sometimes sampling error. You should take notice about it. Sometimes it plays a critical role. And we have alpha error and beta error. We will discuss them in the later class. So the sampling distribution of the sample mean, you will notice in this class, we will discuss many models that goes around the mean and the standard deviation. And the standard deviation plays a huge role as well. The mean will be also the main factor to see if our knowledge can be extracted and the information is significant or not. Since we are talking about the mean, usually there is a mean for the population and the mean for the sample, and we want to make the mean of our sample a representative for our population mean. Usually we hint the sample mean by X bar and the population mean by mu. So let's take this small example. So we have a production line, and this is the earning about your employee. So we have Joe who earns $7, Sam 7, then we have Sue with 8 and Bob with 8. Then we have also Jan and Art and Ted. So if I simply ask you what is the average of our mean population, so simply you will sum the wages and then divide them by the number of employees. But how about if I ask you, this is a small sample, a small population, so you don't need sampling, but just as only for the demonstration. So what are the sample distribution of this size? So you can draw a histogram and see how the samples look alike. How about if we drawn a 2 from this sample? What is the mean? If we just pick 2, it's very near impossible to have the same mean. But is it good enough to be presented for the original population mean? So we want to compare it. So how many samples we can, how many scenarios we have over here? So we have 1, 2, 3, 4, 5, 6, 7. So we have 7 employees. So in this scenario, it doesn't matter if Joe's come first, then Sam come first. So we should have combination, not permutation. And then since we are selecting just only 2, so we have 7 combination of 2, which is equal to 21. Because the order doesn't matter. If the order doesn't matter in this scenario, so it will be end up with 42 samples. So this is the mean population. So we sum up the wages for each individual and divide it by the number of individual. And you can see here, the average is 7.71. Then let's take how many possible samples we can have. And as we increase the number of samples, the information will be complicated. And a very similar problem to that is the traveling salesman problem. So in that problem, we want to reach all the cities in the network, and each of these cities needed to be visited once, and each route will be visited only one. So how many possible combination or how many routes we will using the same formula over here? So these all possible combination. So we might end up picking Joe and Sam, Joe and Sue, Joe and Bob. Also in the other side, we might have Jan and Art, Jan and Ted, and Art and Ted. And you can see for each 2 individuals, they have different samples mean. So for example, for Joe and Sam, both of them taking $7 an hour. So their mean is 7. Of course, this information is outdated. No one takes like $7 a day. If we want to present the population in a histogram, we will see in most employees are carried out by 7 to 8 hours. So we are expecting the mu will be between 7 and 8. How about if we sample for the samples? So distribution of the samples mean will be different. So each mean will be represented more frequently because we are adding just 2, then divided by 2. So we will have something, you can see it's starting creating the bell shape, and we will talk it about later. So let's see how this is work. So we have population of 1 and 2. And we want to sample over 1, 2, and 3. So then we select only 2, the mean will be 1.5. Let's select another one. So between 2 and 3, we will have 2.5. Again, let's select between 1 and 3, then we will have 2. If you want to average the average, it will be the same, the original average. Okay, so if you want to compare between the average of the average and the original population average or mean, so it will be as same. Previously, between 1 and 2, when we have 1.5, then we have 2, then 2.5. So the expected value or the mean or the average for the original population would be 2. How about the average of the average? So the expected value of the samples mean will be also 2. So this is a process called central limit theorem. Okay. So in central limit theorem, so we have the samples, and if they are normally distributed, so they will be approximated to a normal distribution or Gaussian distribution. So if the populations is following a normal distribution, the original population, so the samples should also follow a normal distribution, and we will eventually end up with a normal distribution samples. So if it's not a normal distributions, so it will be approximated to normal distribution if we are talking about more than 10 samples. Of course, the normality applicable for samples more than 25 to 30, we will cross over and see how these will affect our analysis, because we have 2 different standards and each one of them will affect. But why we are talking about normal distribution? So what is the benefit from the normal distribution? So the good thing about normal distribution, we have a formula for it, and it's easier to handle. We can calculate the probability and the cumulative probability distribution from known tables, and many methods such as ANOVA, regression design experiment, need to have the normality assumption before we start do the analysis, and most of the parametric analysis goes around the normality distribution. And even though many machine learning algorithms also need to check up their normality distribution. So there is 2 things you should have it in your mind. So if you have the population normally distributed, then you start sampling from that. The samples should also follow a normal distribution. If you have large samples, but they are systematic, they are symmetric, they are identical distributions, so they're eventually, if they are large enough, their sample will be also goes to normal distribution. And this is will also make many things easier to be handled. So you should make in your mind, so the average of the average is the average of your samples. So in this process, you are collecting different samples and then you average them. The standard deviation of them will be the variance will be sigma squared over n. So let's see what is the properties of central limit theorem. So the expected value will be mu. Then we will have the sample will be x bar bar. Then we will have the standard deviation of sigma over square root of n. Then n will be the number of samples. You can see here, so we have the population from that. So we start 2 samples from it. And then as we increase the number of samples, so it's starting to have a normal distribution shape. Eventually, it will have more normal distribution shape, but you will see the standard deviation is nicking because the number of samples is increasing. So if we have a triangular distribution, it applies to, and also uniform distribution or exponential distribution. So if you didn't apply central theorem, you might have a skewness to the left or a skewness to the right. So the best thing is to apply your central limit theorem where you can guarantee that your mean will be on the center or at least very close to your mean, population mean. Of course, this might affect your standard deviation, but it depends on your focus. And we will learn also another techniques that we can determine the other parameters and the moments. So in statistics, we will have 4 problems. So we might have a high bias, but also with a low variability. So in this scenario, we have a high reliability. So for example, if we repeat the question again, survey it again, or if we implement the same experiment again, we will have the same result, but it's far from what we are expecting. So this is having a problem. Usually in statistics, if we want to achieve a high reliability, there is some statistical techniques like Cronbach alpha or Baird t-test. So like you will have a follow-up survey to make sure that the customers having the same thing, or like you need to have the same experiment repeated 5 times. Then we have another scenario. Then we have a low bias, but at the same time high variability. So people knows what you are questioning about, but unfortunately, they might answering the question in different way. So this is usually under the term of validity, and you need some expertise. So when you're forming your research questions, you need to ask some expertise in the field, and they can help you with that. So you will have a deductive process. So instead of asking a very general question, they will help you out to form a very specific question. And then you will see to what extent you are asking about what you are really asking about. And so this is validity, this is reliability. In this scenario, this is the worst case scenario. So you will have a high bias and also high variability. And then we cannot achieve anything from that. Usually this means like your factors are a noise. And this is the best thing we could achieve. So we are hitting the target at the same time we have a low variability. So in central limit theory, we have the observations of the population, and we want to have a large enough samples that can approximately goes to the normal distribution. As we can increase the sample, that will make the situation way better. So what is the consequences of using the central limit theorem? The first one is we have X bar will be closer to mu, and then we will have the standard deviation will be the standard deviation of our sample by the square root of n. Okay, so let's take an example about that. So we know, for example, if we have n equals 10, so this is the citation for normal distribution. Usually we put to mu, then we have the standard deviation. In this case, we'll have over the square root of 10. And this is the bell shape. So maybe this is the one sample, but after taking 10 samples, so we will have a less kurtosis shape, and this is a more closer to the standard deviation. Of course, the standard normal distribution, the mean of 0 and standard deviation of 1. So this is the tabled normal distribution, and we are trying to achieve that through Z transformation. We will cover it later in next classes. So the population is normal distribution, then the samples distribution X bar is also a normal distribution with the sample size of n. So this is, for example, an exponential. We will see this one in Excel. So please be careful, because this is the exercise of our Excel. So first of all, you will have this formula in your Excel separate sheet. Okay, then you will have also another table over here. So I want you to create a new columns. So you will not having this bar, you will not having this column, you will not having this column, you will have this one. So we want to create this guy. Also, you will have the formulas inside here, and some you will not having the formulas inside the cells. So I want you to make attention what we are doing. So we want to sample from the population that follows exponential distribution with mu equals to 50. So in exponential distribution, so it measures the time between arrival. So for example, if you have a car shop, it will tell you that the time between the first car and the next car will be, let's say, for the sake of this problem, 50 minutes. We have the inverse, which is discrete distribution for the exponential, is the boson. And usually having arrival rate. So what is the difference between bosons and the exponential? In bosons, you are talking about how many customers came within a certain time. In the exponential, you are talking about the time it took to make the surface. So why it's discrete, the boson? Because it's counting. Why exponential is continuous? Because we are talking about time, and the time usually is measured, is a continuous measure. Of course, it can be different measures. So if you are talking about an area, so for example, how much the bacteria are increasing within certain region, what is the rate of them? So it usually measures the time, but also you can use the other parameters. So in the first column, I want you to just build a counting from 1 to 1000. So the easiest way, let's see, this is not here. Okay, so the easiest way, let's assume we don't have this column yet. It's just to highlight the first cell, put 1, and then go to the next one, push 2, then highlight both cells, then hover around the corner. When see it lost, just double click it, then click Control down and see it's 1000 population. So we have 1000 population. After you've done that, I want you to insert a new column, and then here call it random. So we want to generate a random number, and we will cross over this topic and see how this random number, how it's generated. And it's one of the most expensive processes in computation. So one of the problems in high computation performance is generating a random number. In Excel, we just put rand, then open and close parentheses. So equal rand and open and close it. Then double click on it. So this will generate the random, uniform random distribution from 0 to 1. So we're assuming we have this cumulative results. So we want to inverse having the time between the events. So we want to use this formula. So x will be minus of the natural logarithm for 1. This should be inside parentheses. 1 minus the uniform distribution over mu. So you can put here in the reference cell. So this should be your uniform distribution. So minus len, open the parentheses, 1 minus the uniform distribution cell, multiply by your mu. It depends if you are using lambda, so divided by lambda. If you are using mu, so multiplied by mu. So since we are dragging all these numerical values, I want you to fix the mu. So by adding as $sign in front of the letter and the number. So $sign, $sign 6. It depends on your cell. So you should add as $signs in front of your letter, and also as $sign in front of the number of the cell. So it might be in other way placed, but make sure this is only for your mu. Since we are dragging it, then double click on it. So this will generate a random exponential distribution for your population. So we want to fix them. So highlight them, press Control and Shift and drag down. So it will highlight all the data we just generated, because we want to fix these numbers. So press copy and then paste. So it will be fixed. Then you need to calculate the mu for your sample. So this is X bar. And then the sigma for the sample. So this will be the average of your population. And then mu will be the standard deviation. So equals standard deviation also for your population. Let's draw the population and see how it goes. So highlight your population, go to insert, go to histogram and draw it. So we have the population over here. Now use this same information. So this is will collect a random sampling from here, which is use a very complicated formula. I don't want you to memorize it. Just use it, for example, in anything you want, maybe in the future. So this is will just select a random sample from this population. So just highlight the sample over here and then go again to insert and draw the histogram for it. So this is for your sample. Sorry, should be also not X bar. So this should be mu. And this is also the original signal. So this is a mu. So if you want to make this identical, you can play around with the axis. So you can go to the axis over here, format the axis. So let's say I need the width of the bends to be similar. So I want it to be, let's say 15. And for this one also, I needed to have the similar information. So the bend width is 15. So you can see there is some resemblance. Of course, this is a 30 data setup, so no way it can be the same. So this is the sample. After that, I want you to go to the second separate sheet, which is sample. And this one, we have around 10 of these. Okay, so just to play around, let's say this is trial, this trial one. When you push one like that, so it will be changed, but we want to reserve this information. So highlight it, copy, go to sample number one, right click, and save the numbers. Then again, we need to second the trial. So click to, so it will be changed accordingly, but it will stay, you know, exponential distribution. Highlight the sample, copy it, go to the sample again, right click on it, just paste the numbers. Again, we will have the trial number 3, so it will be changed accordingly. Then copy it, go to the samples, and right click on it, paste. And this should give you a general information. So each sample, this is the mean for each sample. And then here we have the standard deviation of each sample. So let's take a look for the formulas. So this will be the average of the average. So this will be the average of all these samples. So this is also the standard deviation for each sample, but be careful, this guy have a different formula. So this will be the square root summation for each one of them divided by the number of these samples. Okay, so the formula will be the first one square plus the second one up to the 10th sample divided by, so we have 10 divided by 10, then we take the square root, then we will have what's so-called the central limit theorem sample for us. And you will see the sample is 48. So it's close enough, and the standard deviation is 48. If we try to increase it, eventually it will also reach a normal distribution, but since we are using 10, so we have a decent, so you can see it changed a little bit, but it's still not a normal distribution. So I want you to go to this website. It is interactive website, and you can try the different effect of central limit theorem in different distribution by changing the alpha and beta. So most of the continuous distribution having alpha and beta parameters, like for the normal distribution, have a mu and have sigma. When you change them, so you will change the shape of the original population and see how it's affected by central limit theorem. So in central limit theorem, our major focus is the mean, and it's have a very practical usefulness in many things. If we take simulation, you will see to what extent this will help us. Of course, it will make the data follows normal distribution, and we can benefit from that doing many other tests, and also we can use it, plug it into, for example, ANOVA or two-way ANOVA, hyper Latin cubic ANOVA, and also other analytics. So how much large? So the rule of thumb is we should have 30 more samples, but also if anything is resembling that, so we are okay with that. Okay, so you can check it using BB plot or histogram or other techniques to see to what extent it follows normal distribution. So in summary, we can say the mean is mu with the standard deviation of sigma